SRU model speeds up transformer with simple recurrent unit, reducing compute by combining RNN with self-attention from transformer architecture. So today, by the way, hello, happy that you're watching this. You can subscribe on YouTube. You can subscribe on my blog. And yes, these will be my notes, quick summarization, distillation, the juice of the papers of SRU and SRU++. I thank to the authors' papers, and as well there is this Yannick Discord meetup discussions. So you can join them as well. And yeah, I was one of them where it was about this particular paper, which is interesting. What is this paper about? So this paper, as I mentioned, suggests architecture that is around 10 times faster than the transformer because it uses very fast version of recurrent neural networks, but as well it combines self-attention, which is a little bit slower but more powerful. How does this work? So there is this graphic here. I have this graphic here on the screen, and basically it works in this way that this is about this is architecture for sequence to sequence or sequence to next token prediction. So input of the model is some sequence of tokens, some embeddings. Each token is represented by a vector. And in recurrent neural network, which is included at the beginning of this SRU++, there's this faster units. But the important is that some first layers are just recurrent neural networks. How the recurrent neural networks work is that they use just one network that is called multiple times for each token, and this networks. This unit takes in as an input the input from the sequence corresponding to the position and the previous unit's hidden inner state. And I do this repeatedly. So in this step, I just get the first position embedding. In this step, I also get the hidden state, which is represented by this blue arrow, and the next token input. And here I get, and for each of these positions, I also get outputs. So I transform the input sequence to output sequence. And I do this recursively. I call the same network multiple times. So this is a recurrent network. In self-attention, this is different. In self-attention, instead of calculating something in a sequence, I do calculation across all the sequence at the same time. What is this calculation? I have this in another post. I will put a link to it in this post where I discuss how this sort of works. It's sort of differentiable key value store, this transformer architecture, right? And what it does is that you compare essentially after some transformation through some key value query matrices, you effectively compare vectors for each position with all other positions. And then based on how they match, you mix up their corresponding values. So you compare each other as all token embeddings with all other token embeddings. If you get a higher match, the more you mix that for the output on that position. So output of attention is again sequence. Input is a sequence. So input of self-attention is sequence. Output is also sequence. So and the self-attention was introduced because it provided faster calculation because of the inherent parallelization of the matrix multiplication that are being done here. And as well, thanks to that, it's more general model. Well, I think in general, it's more general model because you compare everything with everything. You have to add the concept of position, but that's my understanding how was this adopted. Quick note: I'm on my journey to learn more about machine learning, and I feel like I'm getting more seasoned in this area, but it's not. I don't feel like I know everything just yet. So yeah, consider that. So the summary of this paper is that it's about language modeling. So you have input, and then you input text, and you predict next token, for example, next character in the text. Contribution of the paper is that you can increase speed so much with these recurrent networks and using less of the attention that it starts to become imaginable of training your own models from scratch with quite good performance. Authors is this Tao Lei from ASAPP Inc. and people from Google Bay and Cornell. And this post is comprised of this SRU unit, where we talk about what is this new recurrent unit, and this SRU++, where we combine the self-attention with this recurrent unit to get competitive performance and faster training at the same time. There is also this Terraformer paper, which uses SRU and sparsity and many other tricks to get actually even bigger speed up than the standard transformer. But I will not talk about that paper. All right. So, what is this difference between attention and recurrence again? So at the beginning, I described the exact calculation, but in principle, what it is. So it is basically attention versus recurrence is as a difference between a fully connected graph and a sequence. Fully connected graph is more general, sequence is sort of more specific. And so that's why the attention should be sort of slightly more powerful. Why attention makes sense? So if you think about the language, if you know about this dependency parse, well, so the dependency parse concept is basically that you can take most of the sentences in English and decompose them into this tree, right? For example, I prefer a morning flight through Denver, right? I'd like to fly to Denver in the morning. What is happening here? You have a tree, so I have this subject, I have this verb, I have this object, and this object flight. I can further qualify that object flight. I can say that the flight is in the morning. So you get these sort of trees, and you get this tree. Well, basically, the dependence parse here is on the left, and you have also more on this screen. So nice. The sentences are about trees, so that's why some kind of more general algorithm should be helping, right? At the same time, there is the sequence character as well, right? You have this, the sentence goes left to right. We read sentences left to right. So there is the sequence part is also important, but the general one is more important. So the recurrence is about sequences. It only calculates left from right, and it only remembers the previous state. It uses the previous state and the input to produce the output. The issue with the original LSTM, which is this quite a powerful architecture, is that it was less parallelizable because of this sequence characteristic. So to calculate next step, I actually need to have all past steps to do that. So I cannot parallelize across the time sequence, while in the transformer, I actually can do that. So this was the issue. How we can deal with this? So basically, in this paper, this SRU paper, rather small paper, which was got lots of hate on the OpenReview. But this one had this great idea. He was thinking, okay, how do I do this, right? This is the problem. Can I actually parallelize these? If I can do that, maybe I will get the as good performance speed-wise thanks to the parallelization, and maybe there is some benefit of using that instead, because it seems maybe it should be faster than transformer. Transformer is quite complex to calculate, right? So how do you do that? So you cannot do parallelization in time dimension, but you can do parallelization in dimensions. But to do parallelization dimensions, you need to modify the idea of the recurrent networks. You need to simply make relaxed conditions. So usually in recurrent networks, so we use this t for time step, input vector for time step t, we use xt, and the inner state we describe as ct, denote as ct. So if you want to describe, so in the recurrent networks, there's this idea, there's this concept of forget gate, which controls how much information is used from the previous state. And if this forget gate achieves 0, we don't use anything from the previous state. If it is 1, we use some sort of maximum. To calculate this forget gate, we use some sort of sigmoid, which is dependent on xt through, which is through some matrix, and previous state, again, multiplied by matrix, and some trainable vector. So what are the issues for parallelizations here? So multiplication of the input with the matrix is not an issue, because I have the inputs all at the same time and I can parallelize across them. But to actually calculate this element, where I need to multiply the previous state of the recurrent network, I cannot do this ahead. I have to have the all calculated past steps, and that's the issues. But I can parallelize across dimension. I could parallelize across dimension if there is no interaction between the dimensions. How can I make sure that there's no interaction between the dimensions? Well, the matrix has to be diagonal, right? All those dimensions have to be independent. How do I do this? Well, it's not that hard, actually. So you just use this exactly, use dimensional matrix, which collapses the problem into Hadamard pointwise multiplication. And now I can parallelize entire calculation of this SRU, actually. Well, right now, we just demonstrated on forget gate, but in actual, I can then calculate the entire network in 2 steps, parallelizing all calculations. First, I do like big matrix multiplication, and then I parallelize across dimensions in second step using this trick, this pointwise multiplication. That doesn't fully describe the SRU, so let's keep going. So they also use this concept of highway network component. So this highway network is essentially a skip connection. Have you heard about skip connection? Skip connection, basically, you have some network and you'd like to create skip connection. So you, in general, you just add the input. You sort of copy the input and add it after the to the output of the network. And so the gradient can always directly flow around the network as well. And the network sort of has to be adding something. The network actually serves a little bit like sort of like boosting architecture, right? It has to be sort of doing some sort of improvement, or it can be just ignored through the skip connection. And people say it regulates gradient flow. I need to read more on this. But this highway network is more specific skip connection. The highway network actually uses a reset gate. It's like this forget gate in the previous step. But this reset gate in general is used such that you always take the input, which is to skip, to like flow almost directly, and you'd like to add it to this inner state, which comes from the neural network. And instead of just summing them up, you actually multiply both some sort of inversely, right? You take the reset gate, you multiply the reset gate directly with the output, and then you multiply 1 minus reset gate times the input. So the reset gate decides how much we will be mixing the input to the output. The reset gate gives you values between 0 and 1, and it decides the mixing of the output of the network and the actually input. So if the network is not going to help to improve anything, so you can not mix it in actually. So this is the highway component. All equations are written here. They basically are comprised of the two components of this sort of highway and the gate. So the gate always calculates, okay, how much I will be mixing, and the way basically does the mixing. Yeah. So what you do is that you first calculate the inner state, and then you do this, and the inner state is calculated as a highway with the input, and then you do something like this again with where you mix the state again with the inner state to the output. Whereas, of course, in the inner state itself, you use previous inner state. So in this state calculation, I mix how much of the previous state I will mix in with the forget gate, or how much of the current input I will mix in. Then for the output, I will calculate how much of the inner state I will mix in via the reset gate, or how much of the input I will mix in. Okay, so graphically we can see this in this way. This is the highway. So there is the input down here. We can go either through the highway in some sort of short way to the output, or we have to go through the matrix multiplication of the x, which can be done in one step. So I apply matrix multiplications, and then once I have those matrix multiplication, I can calculate this element-wise recurrence. So it is element-wise because it is because it's element-wise, I can parallelize it. You can do dimension parallel calculation. So this is parallelizable, and this second step is also parallelizable. Okay, how is it similar to LSTM? Of course, it's very similar, but the LSTM is more complex. LSTM has this output gate, input gate. We don't have this in SRU. Instead, we have this reset gate, which sort of flip places them. And we have this concept of high-way network, which is not so, I don't see it in LSTM equations. If you want, you can go through the comparison. The idea is very similar. You again have the gates, but the SRU is simply simpler. Okay, why? How can we actually parallelize this? We have 2,000 dimensions. Can you actually in parallel efficiently calculate those? Can you parallel? Yes, on GPU you actually have many cores. So for example, this Tesla T4 has 2,560 CUDA cores. CUDA is this calculation framework, and yeah, this newer architecture has different types of cores. I guess they are faster. But important thing is that the CPU has 12 cores. GPU has thousands, so you can do huge matrix calculations there quite fast. How do you actually do those calculations on CUDA? Yeah, so CUDA has this modification of C++, and what you can do there is that you can say to CUDA, I would like to calculate this in parallel in threads of 1 on cores 1 to n. I would like to call this function in parallel. And then inside of the function, I can then say, okay, first give me which number thread you are, and once I know which number thread you are, I can sum up the vectors for the corresponding dimensions to the output. And in this way, the authors of the paper actually have written their own fused CUDA kernel and implemented this very fast. So the implementation is that they do the single matrix multiplication first. That's parallelizable. Then they do pointwise operation on the single CUDA fused kernel, those gates and so on. Right? They do this in parallel using the thread number. And while the computation is still sequential in the time dimension, they are parallel in the dimension. What are the results for SRU? So SRU slightly outperforms some sort of similar architecture. It's called quasi-RNN. It's slightly faster, slightly better results. But mainly compared to LSTM, which would be CUDA optimized, it is 5 to 9 times faster. So SRU, recurrent network, is 5 to 9 times faster based on the paper and has better results. There is this table over here, and yeah, you can look it up yourself. This SRU 2 layers is basically similar to this QRNN, and it's very fast. If you keep adding layers, you get slower, but still you get even you can outperform even more the QRN. Then okay, SRU++. So SRU++ is this SRU combined with self-attention. This paper is then competitive on ENVIC8 with Transformer XL. Actually achieves state-of-the-art by a small margin, which is impressive with the small amount of compute it needs, because it's 3 to 10 times faster than Transformer XL. It uses 1.6 days on a GPU machine, that's something I can imagine. I can imagine of doing something like training something for 1.6 days on a GPU machine. So that's the data set apparently is rather small, this NVIC8, but it's these are numbers that I can imagine. You can see how it is converging faster on this image, this graph. So how this SRU layer exactly looks. So you remember that previously we had this this input goes to matrix multiplication, goes to elemental wise recurrence. So the SRU++, what it does, it does extra thing. So it does projection to smaller dimension and back to bigger dimension, and then the recurrence. And okay, that's nice. Maybe it helps performance or whatever. But so that's not the focus of this discussion. What you can do is that in this smaller dimension, which can be something like 512, which is manageable for self-attention, you can effectively insert attention layer. Right? What it means? Basically, that if you remember those matrix multiplications, in SRU, you basically replace them with self-attention. It's a little bit more complicated, but that's the basics. What they do is that they don't use any position encodings. They rely basically on the recurrent network layers and the first layers to actually do the position encodings. It operates on the smaller dimension. It uses serial connection, layer normalization. It seemed rather like a normal self-attention with some slight modifications. And what they mentioned that the attention helps significantly. If they add attention, this architecture really helps, is better. But they need much less attention, and that's where they get speed ups. Something like every fifth layer, if they have attention, it does well. It does good enough. Dataset used is this NVIC8 I mentioned it previously. It's character level language modeling dataset consisting of 100 million tokens taken from Wikipedia. This here we measure compression, basically. Well, essentially how well we can predict the next character. So you can imagine that this is a problem for large windows. You need to know a lot of characters in the sentence to actually do the next step. In transformers, this is common problem. The length of the sequence is a problem for transformer because you have this squared complexity. I have one post on this performance paper where this was actually attempted to be solved in different ways. And in this architecture, they solve it by having less transformer calculations, in less layers. They have which is I guess this is the only linear. They can save only linearly, right? Because the squared complexity is still going to be there. All right, this week 103 is another data set. That's word level data set. Again, from Wikipedia, 100 million tokens. That's similar to that's similar to this NVIC 8, except this is a word level. Okay, results. PPL is perplexity. BPC is bit per character. If you saw it in the graphs, basically this SRU++, this recurrent combined with self-attention outperforms Transformer XL while being faster. Right, so it outperforms by 3% BPC. You could say. So that's quite a lot. Yeah, it's not twice better, but it's like quite a lot. And it's very fair comparison. So this comparison is very fair because they use specifically the same byte size, same context size, and they still outperform this. Okay, so then they did analysis how often they need to add the attention into the layers, right? Sometimes they can add it, sometimes they can skip it. That's what the architecture allows. And it seemed that every 10 layers, one attention SRU is enough. So that's where they are saving the time. We can see on the graph here that the GPU hours are sort of going down the less attention layers we are including. And yeah, I think it should be going down like basically linearly, because you are sort of throwing away some compute, Well, actually, you are dividing the compute by 10, something like minus. Yeah, okay, never mind. So the compute goes down as you have less attention. While BPC is getting worse, right? But it's amazing that even if you have for the speed comparison, even if you have every layer the attention, it's still 10 times faster, and then it gets even faster if you start including attention less, right? So it's 10 times faster than Transformer XL. Okay, they also achieved state of the art on NVIC 8, which is rather a small data set apparently, but it's still interesting. And yes, basically the previous state of the art was feedback transformer. I haven't mentioned this paper is from 2021. All right, and yeah, and at the same time, compared to, for example, Longformer, they have 1/10. 1/10 of the GPU days. That's amazing. Okay, they even say it here, right? Our results are obtained on AWS with 8 GPUs. Reported training time. Okay, whatever. max performance on VIC 103. So they haven't achieved the state of the art on this dataset, but they are worse. They are sort of on par with compressive memory, which is compressive Transformer XL modification. They outperform Transformer XL, but they haven't outperformed this other benchmark. But they are still very competitive. The speed comparison as a final result is that this SRU large, achieving complexity similar to better than Transformer XL, worse than KNN LM, has huge speed, right? Again, several times faster than Transformer XL, and sort of on par with Shortformer, but better results. And if you include even less attention layers, then you outperform Shortformer while still having very good results. All right, that's all for today. This was the SRU++ paper. I hope you got the gist, some idea of the paper. I continue to learn more. I would like to see you again in the next video, so you can subscribe, and see you next time. Bye.